climate. Okay, and that is something that we are going to see how it's interconnected with eco-hydrology, right? And probably how does it get affected with, how climate change affects some of the, how some changes in land use, land cover can change both climate as well as the ecosystem services. So, at the end of this lecture, we will be able to understand the concept of climate change and its variability in both space and time, impact of climate change on eco-hydrological cycles, assess the implications of vegetation and land use changes on climate regulation. So, at the end of this lecture, we at least will be able to take home these points. So, climate change, as we said, refers to long-term shifts in temperature and weather patterns, something that you see. If you just Google some images, you will see these kind of pictures, emissions, then these are mostly wetlands, extreme events, right, such as cyclones, pollution, solid waste management, and agriculture. Now, climate change is caused by greenhouse gas emissions, right, where these emissions are trapping the heat and which is actually increasing the temperature. Now, these emissions are coming from various sources. It's not one source, it is transportation. You have transportation, you have fossil fuel consumption, right? Energy production. Many of your thermal power plants, they have the coal-led thermal power plants emissions. Industries, agriculture, and land use changes. So, all these have greenhouse gas emissions, and it is approximated that compared to pre-industrial times, it's approximately 1 degree centigrade. Now, there is something that we need to understand, that climate change is a natural process, right. In addition to that, some of the natural processes do also impact, right. For example, volcanic eruptions, they also release lot of greenhouse gases. Okay. So, in our anthropogenic activities such as these do increase the rate, right, at which this climate change is happening. Okay. So, we are basically facilitating it to have a much faster change as compared to what it would have happened. So, you have different temporal scales. I think the slide is not visible a little bit, but it's fine. I'll just explain. So, you have temporal scale, you have a small temporal scale at seconds, turbulence, weather parameters. These boxes are weather parameters, and these dotted lines correspond to hydrological aspects of it. Then you have thunderstorms, sea mountain breeze, hurricanes, which go up to couple of hours to couple of days, right? Cyclones, long waves, westerly trade winds, more longer time period ENSOs and climate variation, right? And your GCMs are able to simulate these aspects at a coarser time level, starting from some days to future years. Hydrological perspective, whichever are happening at smaller time scale, in minutes to days, you have urban flooding. Sometimes from hours to weeks, you will have flooding in the basin, river basin discharge. In terms of irrigation, the changes that correspond at a longer time scale from weeks to month affect the irrigation, and then from months to years, you have water resource management, and finally the climate change impact, right. Now, these changes are happening differently at different spatial and temporal scales. Some places there is an increase in precipitation or increase in extreme events, in some places there is a decrease, right. So, both at spatial scales that refer to the geographical extent of your climate change, ranging from local to global levels, and it is affecting different locations differently, right. So, it is not one solution that fits all the places. So, your temporal scales involve duration of timing of extreme events, which range from short-term events such as El Nino to long-term trends observed over decades or centuries. Okay. And the variability means that climate change can manifest differently across locations and at times. Now, IPCC, in the recent report, it says the global mean surface temperature correlates closely with the cumulative greenhouse gas emissions, right. That is something that has been there. And the internal climate variability such as ENSO contributes to, so there are various studies which, rather we have lot of information based on these global parameters right, such as ENSO and all these parameters. And based on that, we can predict whether we have a normal monsoon, above normal monsoon, or below normal monsoon, right? On an average, we can predict that. Now, coming to the Indian data, you have data starting from 1901. In some locations, you have before 1901, but the gridded data that we generally use, which is a reanalysis data, which starts from 1901 to 2010. Now, in this period, what they have observed is across India, or on an average across India, the mean temperature, maximum temperature, and minimum temperature, that is the annual time step, has increased by 0.15 degrees centigrade per year, per decade, sorry, right? And that means the temperatures are increasing across India, okay? But we have also seen that it's not consistent, especially some locations it's increasing, so it's an average value. You don't take it that the entire India it's increasing 0.15. Some locations it's much more higher, some locations it's not, right? And these increasing trends are observed more in pre-monsoon, that is in the summertime and post-monsoon time periods, right? And in some locations in the monsoon season as well. This is a figure that came in newspaper where last year 2023 the temperatures, they plotted 1979 to 2000, all the temperatures here, and both 2022 and 2023 both were at the top of your ensemble and saying that the temperatures are increasing. Now, many studies they attribute this particular rise as climate change. So, is it climate change? Is it because of climate change? Can we say that? 2023 was really warm. So, is it because of climate change? Can we say that climate change has caused this?
Not exactly, because you have some other bodies like the aerosol concentration increases, some of the variables which drives the climate change. So those concentration increases for a particular year will go higher emissions. So we can say that causes the warming rather than the climate change.
Okay, you say that there are other factors in addition to climate change. Okay. Anyone else?
So 2023 was a El Nino event. So most of the Australian and Indian subcontinent there was a high temperature as usual, and also its impact the African countries as well.
Yeah.
So that is maybe the one of the reasons we have. And again, climate change that increased the frequency of the El Nino. Usually in 2 to 4 years, it usually happens. Generally in 3 years. But as the climate change increases the frequency, maybe that is what.
Correct. I mean, yeah. So, if it increases the frequency, then we say that there is a change in climate, right? Though there are studies now which try to attribute whether a particular event may or may not have happened because of climate change. There are different studies now, but it's very difficult to attribute one particular year or one particular event to a climate change. When I say climate change, when we started, we said it's a long-term shift in your climate patterns or weather patterns, right? And taking one data point on an average and say that, okay, this is because of climate change may not be accurate, right? And that's where you say when you do this GCM projections and project it for the future, you cannot pick out that I will get this much maximum flow. You say that if on an average there is an increase, this much increase or this much decrease, right? It never corresponds to a single event, right? Now coming to the temperature changes, something that has been plotted. So in the recent times, starting from the 1980s, there is an increase. That's what we have seen, 0.15 in the annual mean temperature, 0.15 in the annual maximum temperature, and 0.13. And the future projections from the GCMs also show that the midterm and end term periods, there could be a rise of 1.39 to 2.70, right? There, we are expecting the temperatures to rise across different projection scenarios, right? So in the different SSPs, we on an average we expect it to rise between 1.39 to 2.7 and 1.3 to 2.44. Now, in this process, it's not only the temperature rise, but also some of the extreme events such as heat waves, intensity, duration and frequency of your heat waves, and also the area of coverage, the geographical extent at which it is going to come, are projected to substantially increase throughout the 21st century, right? And all these are projections. Again, when we talked about the feedback system, it considers some sort of feedback, right? And that feedback may change depending upon some of the anthropogenic activities that we are taking up. Now, this changes in water, what can you expect? Let's say this change in temperature in terms of water and ecosystem, what changes do you expect? Evaporation may increase, but evaporation is a cooling process. It cools down. You know that evaporation is a cooling process. It takes the heat and cools down the surrounding. Convective precipitation, yeah. So the moisture holding capacity, as he said, that it increases based on the temperature. The moisture holding capacity increases, and then whatever, it may change some of the precipitation patterns, right? And that is what we are going to see in the precipitation patterns as well. Precipitation changes in India. This is the, what you say, if you consider this to be mean, this is the positive and this is the negative. So normal and above normal is what we were seeing. Excess is plotted as green, deficit as red, and normal as black monsoons, right? Whichever is the black is the monsoons, normal monsoons, green is excess, and red is deficit. Now, if you see here, in the recent years, we are having largely deficit monsoon, and this is also across India. It's not necessary that a particular location is having a more deficit monsoon, right? In the last 5 years, I'm here, Warangal, it's always received more than the normal monsoon. In last 5 years, the annual average of Warangal is 1100 millimeters. But last 5 years, we have received more than 1100 mm each and every year. Okay, some of them slightly higher, which will which will correspond to the normal conditions, but in general it was excess, right? But on average, you can see that there are increasing years with reduced precipitation, right? So historical climate records indicate abrupt changes in Indian monsoon precipitation over decadal and centennial timescales. Okay, so they say that from 1951 to 2015, there has been a decreasing trend in all India annual and summer monsoon rainfalls, right? There may be some decrease. Even if there is no decrease, right? Let's say you are receiving the same amount of water, the characteristics might change. Number of rainy days, right? You may receive the same rainfall in less number of rainy days, or you may receive same rainfall in more number of rainy days. So your number of wet days, number of dry days are decreasing or increasing, right? Depends on the location. So the changing precipitation pattern at both spatial and temporal scales are expected to add water stress, right? You have planned your water infrastructure. Our water infrastructure is planned in a certain way. You have a lot of structures, and from there you expect to supply domestic water requirement, you expect to have hydropower, and you expect to supply to the agriculture. Now, in this changes, whatever is happening, it will change the inflows to that particular structure, right? It may increase, it may decrease. In that process, your management plans are also, right? For example, Hyderabad takes water from Nagarjuna Sagar. It draws the water, it pumps the water from Nagarjuna Sagar. There is a constant supply. Now, if the changes in Krishna basin or in the upstream have some certain changes, and Krishna is a river which is largely regulated. It has dams at every possible location. Now, that reduced inflows will affect the inflows to Nagarjuna Sagar, right, from the Srisalem and down, and in that process, it will have an effect on domestic. So, the rainfall patterns may be changing at some other location, but its effect may be felt at other places. Okay. And among the agriculture, your rain-fed agriculture is expected to be worst affected by changing precipitation patterns, because it primarily depends upon the rainfall, and if you don't receive sufficient water during critical crop growth stages, it becomes challenging to have the crop yield, right? So, in certain stages, probably before the flowering, if you don't have certain amount of irrigation that is happening, your yield is going to drastically reduce, and that is where rain-fed agriculture. Anyone has an idea how much of our area is rain-fed in India? Close to that, 50 to 55%, right? 50 to 55% is still under rain-fed agriculture, okay? And this rain-fed agriculture is important for our food security, right? And we have kind of exhausted how much area we can add for irrigation. Probably with the river interlinking, we may add little bit more area, but we are more or less saturated with adding more area to the irrigated agriculture. So rain-fed agriculture becomes important for us to have the food security, because 50% area, which also contributes to 50% of the food production. Okay, so rain-fed area is something which is going to be one of the worst affected with the changes in precipitation pattern. Increase in precipitation intensity causes flooding, impacts water resource system, and at the same time it also causes drought. Now, your drought, it affects your water resources availability as well as the agriculture, but it also depletes the groundwater. We start extracting more water during the drought season, and at the same time the recharge reduces. So it's a double side. The recharge is reducing, you're extracting more water, and the groundwater depletion is a cause of concern. Now coming to the changes in carbon dioxide level, the emissions that you have. So these are the different sources. The coal has these many emissions, oil, natural gas, and other sources, right? So carbon dioxide emissions are some of the things that are driving the climate change, and as per the Paris Agreement, we expect to achieve net zero by 2050, reduce our emissions by 45% by 2030 to keep global warming level at 1.5 degrees centigrade. So scientists have worked out that if we don't reduce it to these levels, our warming is going to go beyond 1.5 degrees centigrade, and most of the countries have agreed to achieve these targets, to achieve a net zero by 2050 and 45%, right? Now, these emissions are rising global warming, which is changing your hydrological cycle and crop productivity as such, right? But then, in addition to your hydrological cycle, your eco-hydrological variables, crop productivity, the crops are going to behave differently for different emissions. We are going to talk about it a little bit. So these are the measurements from one of the locations in India, in the Western Ghats, where carbon dioxide emissions were taken up. And then what they observed was the behavior is different at different locations. Some places which were expected to be the carbon sinks were emitting during certain point of time, and they were drawing out at other points of time, right? So basically the afforestation, which helps us in carbon sequestration, the behavior of that varies from location to location, right? So the carbon dioxide emissions which were there in India, they showed, and this was also observed by satellite data, right? The carbon sequestration, carbon sinks have been are there since 1980s because of afforestation, but their behavior have been varying from one point to other point, right? So flux tower studies show that carbon sequestration in Indian forest varies with different ecosystems reaching their peak at different times of the year, right? Now, can we simulate that in any of our models? Is it possible? Probably yes, right? You have certain data, you can develop a model. Is it possible? Whole point of this course is yes, to make it possible. Okay? Okay, and then one of the things is sparse distribution of greenhouse gas emissions limits our understanding of these dynamics. We need more sites to have a clear understanding on these processes. Okay, so as I said, the increasing temperature of atmosphere increases the amount of water vapor a air parcel can hold. Now, why is this important? Any idea? Captures the heat, yes. Yes, it's a cyclic process. It will increase the extremes. How?
Keep on holding water for a long time. So suddenly it gets burst and it will get like in terms of 2-3 days hold time, it becomes in hours.
Okay. Anyone else? How does the precipitation gets formed? How do you get precipitation? So essentially your air parcel which has water is adiabatically cooled. It gets adiabatically cooled to reach to a level of saturation. Now if your temperature is higher, that saturation, the volume is going to be much more higher. Now in addition to that, our aerosol concentrations are increasing because of the pollution and because of the emissions as well. That means it has more ability to condense. So once air gets saturated, if it has aerosol particle, the water vapor condenses on these particles. And when it reaches a sufficient weight, it comes down in terms of a precipitation. Now the air parcel has large volume of water and large volume of aerosols. It condenses fast, the weight will increase and it will come as extremes, right? So the water vapor which it is holding, the increase in water vapor, as he said, it's a positive loop. It also increases the temperature and at the same time it also increases the extreme precipitation as well. Okay. Now in addition to that, your hydrological cycle undergoes transformation because of these extreme rainfall events that redistribute water resources in both time and space, right? Your shifts in monsoon period may have certain effect. It can directly affect evaporation and runoff patterns, resulting in more extreme weather events. The microclimate will also start getting changed because of changes of global cycle. And it is also affected by changes in CO2 concentration because elevated CO2 levels are going to have an effect on metabolism of your plants, right? Enhanced CO2 will have an effect on metabolism of your plants. Any idea what kind of changes will happen in your crop with increased CO2? We have talked about water and nutrients and temperature. But what happens if your CO2 increases? Capacity of the photosynthesis increases. Okay. Anything else? Pores of the leaves get choked by? Okay. Sorry? It has an effect on evapotranspiration. Yeah, I'm saying that how does this CO2 affect the metabolism of plants? Yeah.
The harvesting time will increase, but the height of plant and the nutrition level will not be that much.
Yeah, correct. Well, yeah. Now, the effect of CO2 varies from plant type, right? It increases the photosynthesis in your C3 crops, and C4 it reduces. C4 is basically your maize, sugarcane, these crops where it does not have any effect. But the C3 crops such as your rice, it increases the photosynthesis, and as I said, the nutrients reduce. So the quality of the crop reduces, though the yield and biomass will increase, but the quality will reduce, right? And that is what. So there was some experiments which were done using free air carbon dioxide enrichment that indicated that CO2 can enhance photosynthesis by about 40% on an average, while reducing stomatal conductance by 22%, resulting in decreased water use. Now, what this does is, if you reduce the water use, we go back to what is the function of water in a plant. it cools down. It helps to keep the temperature regulation. And that way the plants face. It plays the water loss in hot and dry environment. So plants tend to dry out, right? It leads to increased dry matter production and crop yields for C3 plants, which primarily utilize an enzyme called ribisco to fix carbon dioxide into sugars, right? But then C4 plants such as maize and sugarcane have evolved mechanism to minimize photorespiration by concentrating CO2 around this, right? Allowing them to conserve water and thrive under challenging conditions, right? We have 90% of the crops are 80 to 90% of the crops are classified under C3 and C4 are quite less. Okay, a figure here. So your elevated CO2, it had some changes in the biochemical levels such as chlorophyll, flavonoid, antioxidants, and then leaf water content, right? And at the same time, it has morphological and physiological changes: tomatal conductance, photosynthetic rate, seed size, density, and root surface area. Okay, so as they said, elevated CO2 can lower the nitrogen and protein concentration in plants, affecting food quality. And the photosynthesis efficiency to improve food security in a changing climate is something that we need to see. So some research is going on how to improve the C3 crops by seeing how C4 adjusts to the CO2 concentration. It does not increase the biomass, it does not reduce the water loss efficiency. So can the strengths of them can be integrated, right? So the current projections of CO2 also indicate that atmospheric CO2 level predicted for 2100 will significantly impact plant physiology and growth. Okay. Obviously, your gross primary productivity, which is your ecosystem service, they also reduce changes in the climate change, right? So climate change disrupts your gross primary productivity by altering growing seasons, shifting species distribution, and modifying water availability, which finally transforms the ecosystems and carbon sinks to different sources. Okay? So then you have these changing precipitation patterns and increased evaporation that can lead to a decline in groundwater recharge, posing long-term water scarcity challenges for communities that rely on aquifers. Okay? If you are predominantly dependent on groundwater and these changes are causing a change in your groundwater recharge, those areas are much more vulnerable. Okay? Now coming to your impact of vegetation and land use on climate regulation. We have seen this figure before, right? A forested area, it has a microclimate, it is more regulated. So what happens is you have a solar radiation, the albedo is low, there is a low sensible heat flux, and there is a high evaporation, evapotranspiration, which actually cools down the atmosphere, right? But in a deforested area, there is a lower evapotranspiration, but it also does not cool down because of the lower evapotranspiration. But there will be a higher heat loss, sensible heat loss to surface and atmosphere, right? And these land use, land cover changes affect the global climate through various biochemical and biophysical processes, right? So this is one example of a forested catchment which has, but it may have other effects on the microorganisms and animals. Okay? And also agricultural practices can help mitigate extreme heat extremes through increased evapotranspiration, but sometimes they also cause this climate change. Okay? Now you have a figure here which causes different land use, land cover change. The red color is carbon dioxide emissions, the orange is methane, violet is nitrous oxide, and blue is NOx, and the green is aerosols. So these are different natural environment processes, natural fire cycle, forest fires is also a natural process. Now it increases all, and because the plants are there, some of the carbon dioxide will get assimilated. Wetlands, they sink the carbon dioxide, but they release the methane. Forests, they balance it out based on the assimilation and the respiration. But when it comes to anthropogenic activities, you see that there will be changes. This irrigation, everything gets increased, right? Deforestation, this is increasing. Your aerosols are reducing, which will have an effect on all the factors. Reforestation, it is a sink that is there. The carbon dioxide is sinking. but then other places such as pasture and agriculture increases those particular aspects, right? So the shifts in land use, land cover have a significant effect on land surface, water, energy, and carbon fluxes, right? It has a significant effect on these fluxes, which can modify local and regional air temperatures through changes in atmospheric circulations, right? These fluxes have a change in the atmospheric circulation, and which will have a significant impact on global climate. Now coming to a case study which is done by Sibin et al., Professor Chaube's group, where they looked at the influence of bioenergy crop production and climate change on ecosystem services. Now sometime back in US, they had a regulation which said that they will move from a more fossil fuel to a more bioethanol, ethanol based fuels, right? And for this ethanol based fuels, you need some raw material, which is basically the starch of your plants, the glucose, which our plants had high glucose contents. So there is a starch content. They are good raw material for ethanol production. Now, one of the raw material which was considered was corn stover. Yesterday we talked about that maize is usually left on the fields. I mean, you remove the yield, you remove the maize cobs, and the plant remains on the field. Now that helps in different ways. It helps in reducing the erosion. It keeps the nutrients as it is. But the corn stalk has good content of starch, which can be a good material for this ethanol production. So people started removing that, leaving the field open, leading to water quality problems. And that is where a solution came about the miscanthus. You saw in the yesterday's ecosystem services, miscanthus and switchgrass, which have good content and can be used for ethanol production. But then how does this land use pattern change affect your ecosystem services is something they looked at, and the climate change as well across different scenarios. Okay, so if you change the land use from corn soybean rotation in your San Joseph watershed, how does it affect your corn and soybean are used as food. Now you are removing them, growing miscanthus, which is primarily for the fuel. So that also is a challenge that needs to be addressed. Many studies from Professor Chaube's group came on optimizing these land use patterns, right? But then, and that's with that premise, they looked at to see how these factors affect, okay, and what kind of adaptation strategies can be developed. So they checked it on two watersheds, San Joseph watershed, the watershed that we are delineating right now, or we are working out, as well as Wildcat Creek watershed. This is the state of Indiana, and then you have San Joseph here, you have Wildcat Creek here. Okay, so the area is more or less similar, around 2,000 square kilometers for Wildcat Creek and San Joseph River, and both watersheds consist of fertile soils and receive little more than 1,000 mm of rainfall annually, right? Wildcat Creek has 70% of corn soybean rotation, and San Joseph has 37% of corn soybean rotation with a 25% pasture land, right? So Wildcat Creek has more agricultural area as compared to San Joseph. So they use SWAT, and to one of the things they have done is they have modified the SWAT to incorporate the miscanthus and switchgrass crops within the field, right? And then they used the GCMs, the CMIP3 scenarios. This was back in 2017, where they had A1B, A2, and B1 scenarios for the future climate projection from 2020 to 2049 to look at what are its effects, right? In general, any GCM model when you use, you need to do bias correction and statistical downscaling because of the course of the resolution, and these are mostly regional applications. So in these regional applications, both were employed to improve the climate projections, and the analysis indicated an expected increase in average monthly temperature and precipitation in future compared to the historical periods, right? And the overall objective was to quantify ecosystem services of potential bioenergy production scenarios for two watersheds and to assess the variability in these services resulting from climate change. So there were 17 bioenergy scenarios, 17 scenarios that was using miscanthus, upland switchgrass, and corn stover. in 2 watersheds. There were different land use classes, marginal, pasture and agricultural lands. So based on these 3 crops and these land uses, 17 scenarios were developed, right? And as I said, the SWAT was modified to simulate these bioenergy crops, and the model estimated ecosystem services, something that you have seen. We can use SWAT to at least quantify the ecosystem services, right? So specifically freshwater provision, food provisioning, fuel provisioning, erosion regulation and flood regulations. So these are the 17 scenarios which you have. Scenario 1 to 17, you have miscanthus in the marginal land, switchgrass in the marginal land, miscanthus in the agricultural marginal land, switchgrass in marginal land, so on and so forth. And there were some scenarios where they said that, okay, instead of converting the agricultural land, why don't we convert the pasture area into some of these bioenergy crops? And they developed these these ecosystems provisioning, which you have seen earlier. Now they developed the baseline scenario, the original scenario, the baseline scenario that was existing, and assessed the ecosystem services, and they compared between St. Joseph to Wildcat Creek, right? So generally your St. Joseph River had exhibited strong freshwater provisioning, which reduced in Wildcat Creek because of intensive cropping pattern of about 70% area. And because more area was agriculture, sediment concentrations were significantly higher in Wildcat Creek as compared to the St. Joseph. And since more area, more utilization of nitrogen and phosphorus fertilizers, and both watersheds displayed low flood regulation services, but erosion remains within the tolerable limits, right? And food provisioning was slightly higher in St. Joseph watershed, while fuel provisioning was estimated at 0, but both due to the focus on second generation fuel. The fuel that the miscanthus and switchgrass or corn stover comes from so the baseline, it was assumed to be 0. So after they put it, they observed that in Wildcat Creek, miscanthus cultivation on high slope areas, corn soybean areas resulted in a 21 million gallon production food biofuel production, with 8% reduction in food provisioning and enhancement in freshwater provisioning and erosion regulation, right? So addition of miscanthus and switchgrass reduced the pollution, regulated the erosion and improved the freshwater, but it had a reduction in food provisioning. It had almost 8% reduction in food provisioning, right? And the choice of crop affected the fuel provisioning, with miscanthus yielding almost double that of switchgrass, right? So each crop or each, even the corn stover has some calorific value, right? So depending upon that, the miscanthus has more fuel provisioning as compared to your switchgrass, right? So based on that, they found out that while bioenergy crops can significantly boost fuel production and ecosystem services, they also require careful management to mitigate reductions in food provisioning, right? So it reduces your freshwater, or it improves the freshwater provisioning, it increases your fuel provisioning, but your food generation reduces, right? And based on this, lot of land use optimizations were performed to identify which areas, so that there is no reduction in food and fuel consumption, as well as maintaining the nutrient balance in your streams, right? And they also assessed changes in ecosystem services under climate change and bioenergy scenarios using 9 climate projections. And the baseline scenario indicated a 9% reduction in food provisioning for the future period, 2020 to 2049, compared to 1960 to 1989. Right? And bioenergy scenarios mirrored baseline trends, with food provisioning changes consistent at around 9%. Flood regulations showed slight improvements under certain scenarios, right? But then there is a slight greater decline in fuel provisioning than miscanthus when you were using it as a switchgrass. So these are some of the scenario indices, all the 5 ecosystem scenarios. The A figure compared to the baseline, where all marginal land, right, which was susceptible to erosion, were converted to miscanthus. B, all pasture area converted to miscanthus. C, 50% stover removal. So instead of removing the entire stover, you just remove the stover removal, right? This is compares. And then last one, random and strategic conversion of 50% corn stover area to miscanthus. You wherever you had 50% removal, you convert into miscanthus. And you see that they had estimated different cases for different periods. This was the past, 1960 to 1989, current 1990 to 2019, and for the future period. And as you see here, compared to historic, most of the provisioning services was reducing with changing climate, right? And depending upon the condition, each of them were behaving differently. Similarly, for your Wildcat Creek as well, the results were similar. From the past, all the provisioning services were decreasing, right, in all the 4 scenarios. And again, depending upon which condition you are choosing, you had a variation in your provisioning services. Okay. So again, the flow diagram that we have seen, this is the baseline and this is miscanthus in high slope areas. You see here there is a improvement in the fuel provisioning and there is an improvement in the erosion regulation, right, in both the cases. There is a slight reduction in food production, food provisioning index, but in general their fuel provisioning and other factors improved. So this is a comparison of all the 17 catchments for different indices. Some of the indices were higher for Wildcat Creek as compared to the San Josef because of higher agricultural area, but this was in general what was observed, right? A indication between 2 catchments in the state of Indiana. So to summarize, the study utilized SWAT model to evaluate the ecosystem services for different bioenergy crops. We need to understand the climate change, right, and at the same time try to see how these adaptation strategies, basically using scenario analysis, how is it going to affect various ecosystem services, hydrology and ecosystem in general, right. So much of the scenario analysis will help us in taking a more prudent decisions, right, which will be sustainable, right. Much of this sustainability comes from this scenario analysis. So key findings from their study that increased agricultural area decreases freshwater provisioning, perennial bioenergy crops boost freshwater provisioning and erosion regulation, constant over removal for bioenergy has minimal impact on other ecosystem services, flood regulation is less affected, and high slope areas benefit significantly from perennial bioenergy crop production, and land use changes have a greater impact on ecosystem services than climate change, which mainly affects food and fuel provisioning, right. So the take home message is the climate change has an impact, and the changes in our agricultural practices as well as the land use changes will have an impact on the climate feedback with the changes in evaporation, evapotranspiration, and the hydrological cycle intensification as such, right. So for developing any solutions, it's always good to have different scenarios, and those scenarios can be implemented, right. Okay, any questions before we start the next lecture? Yeah.
When we are quantifying the services, if we are considering the genetic services like biodiversity, how do you quantify that? Considering biodiversity services is very complicated.
In this case, probably we cannot, right. This was mostly done using SWAT models output, and genetic service is difficult to quantify that because SWAT model in itself does not consider the biodiversity. It does not simulate the biodiversity or the plant, the animals and other microorganisms. So that has to be done separately.
We can relate it to some other parameters.
Probably we can relate. We can develop a relationship between some of the biodiversity factors with, let's say, water quality factors. Take the historical data and develop a relationship, and probably use that as a surrogate model to have what we call it, like using the census data or something to have a genetic provisioning service.
How reliable is this SWOT output, and we can rely on that software for our future? Is that okay to go this software or using some other software?
Basically, you're asking how reliable is the model, right? It all depends on the person who is using, right? So it's like you should be knowing about your watershed, what is the input you are giving, and whether the output is making sense or not. right? It's a tool. Finally, model is not something which is going to give you all the solutions. Any model, whether SWAT or any other model, is a tool. So if you are giving a good input data and you are seeing that my process representations are good, it is reliable.
Sir,
But
in terms of publications, they generally mention the source of data,
Yeah.
not the data, in the most of the cases. So how it can be something in black box?
no, there is no black box. See, I think now most of the publications ask you to share the data in different repositories. Most of the publications are asking you to do that. But if you are collecting the data on your own, you can always say that you have collected the data. Need not be a black box, right? That is the whole point. In terms of publications, well, what I believe, if you do good science, publications will follow. So if you are trying to solve a problem and if you are trying to address some issues, then the result and publications will come automatically. Okay, there are two things. One is working for a publication and working to solve a problem. If you're solving the problem, probably you'll get the publication. Right? So reliability, it all depends. So if you just give some data, get some output, I'm not sure. But you should make sure that your model is working well. Model is meant to do what it has meant to do. Right? If you use it as a black box, I'm not sure, but if you know what is happening, then you can make out of the results like whether some process is there or some process is not there, right? And it goes back to what I said. Any model is a simplified representation of a real world system. It's very difficult to mathematically represent the entire system with all its complexities together, right? And that is something that we have to consider. So in that frame, how do we work out is something that you can think about. Any more? No questions? Thank you.
Okay, how is everyone? Still good? Okay, why don't you all stand up? You have been sitting there for last 1 hour, right? Let's do a little breathing exercise. It will freshen you up. So lock your hands like this, right? Inhale, and when you are exhaling, then pull it in opposite direction, right? So inhale and pull it when you are exhaling, not when you are inhaling. Let's do it 5 times. How did it feel? Nothing? If you start doing it regularly, and before you go to your difficult meeting with your advisor, and do this before you go, you will be a lot calmer and you will have a clarity of thought. Anyway, have a seat. I'm sure this is the part you all will remember for the longest. Right, so how many of you have heard about Sustainable Development Goals, the United Nations Sustainable Development Goals, SDGs. Okay? Some of you, what are they? Water and sanitation for all is one of those. Yeah. Zero hunger is another one. Yeah. Empowering women. Yeah. And so many countries have adopted that as a framework for development. And what in next few minutes I will talk about is how some of the tools and skill sets that we have been talking about here can be utilized to evaluate sustainable development goals, at least some of those sustainable development goals. And so at the end of this lecture, I expect you to understand the concept of sustainable development goals as put forward by United Nations, to discuss the solutions and strategies to maintain sustainability for these goals 2, 6, 13, and 15, using some of the case studies that I will talk about. And you should be able to discuss the key sustainability challenges that are related to water scarcity, climate change, and land use changes. So these are 17 goals, right? And if you have not seen it, take a few minutes when you go back today or tomorrow or this week to familiarize yourself. This is something good to know. India is investing a lot in making these a reality, and so are many other countries. No poverty. These are big goals. Zero hunger, good health and well-being, quality education, gender equality, clear water and sanitation, affordable and clean energy, decent work and economic growth, industry, innovation and infrastructure, reduced inequalities, sustainable cities and communities, responsible consumption and production, climate action, life below water, life on land, peace and justice, strong institutions and partnerships for the goals, right? These are all really laudable goals, and these are all created to bring prosperity, quality of life, peace and harmony within a country, among the countries. And if you go to the website, it has detailed reports about each one of those. What does it mean? So these promote a holistic approach to development and emphasize the interconnectedness among the global challenges. Water and sanitation is tightly linked with the health and well-being, which is tightly linked with zero hunger. Crucial for promoting global development and ensuring a sustainable future for everyone. These sustainable development goals aim to create inclusive societies, right? Gender equality is one of those. And reducing inequalities for all is second one. So it is meant to be very inclusive. When you talk about zero hunger, so that includes everyone. They also serve as a catalyst for innovation, driving technological advancements in various sectors. And they play a vital role in promoting peace, stability, and prosperity for a just and equitable world for all. To me, these serve as a constant reminder to what we all should be working at. And I frequently go to the website and I look at it. I look at some of the reports that come out regularly. I read papers that relate to these sustainable development goals. So when you look at that and you look at in the context of eco-hydrology, right, what can you contribute? What can you work on? There are specific goals. Goal 2, zero hunger, that aims to end hunger and achieve food security. We have been talking about food production, right? We have been talking about ecosystem services and food provisioning as one of those ecosystem services. We have been talking about modeling and how you can use the modeling models and tools to evaluate how much agricultural production takes place in a watershed. Clean water and sanitation that seeks to ensure sustainable management of water and sanitation for all. It's a big goal. It's a very difficult goal. If you look at the history of mankind, water is number 2 source of conflict. If you look at the battles and conflicts and wars that are happening within the societies between countries, water is number 2. And it goes as far back as history of humans. Climate action focuses on urgent measures to combat climate change and its impacts. We have talked a lot about climate change this week. And then life on land and life in water, right? Both promote management. So life on land promotes the management of forests and reducing or eliminating biodiversity loss. Life in water is an important part of food production, as well as providing genetic resources and biodiversity. So some of these goals, the tools that we have been talking about here, and if you continue to work on these tools, you will be in a position to make a difference and contribute to these sustainable development goals. So zero hunger, right? It aims to achieve food security and promote sustainable agriculture and emphasizes the need for comprehensive approaches to ensure access to safe, nutritious, and sufficient food for all. What is happening is you look at any society, whether it's India or US or anyone else for that matter, and malnutrition and obesity coexists in the same society. You see people suffering from too much caloric intake, and you see people suffering from not enough nutrition and calories. And it doesn't matter whether you are a hydrologist or ecologist or engineer or social scientist. It's something that we all should be working on. What can we do to eliminate hunger? Has anyone, well, let me not ask that question. To achieve this goal, it is essential to enhance agricultural productivity and resilience and invest in rural infrastructure. So rural infrastructure investment is important, right? Average land holding size has been reducing globally, and majority of the agriculture is done by women. So what can we do to bring the technological advances to make the job easier? Because they also carry additional responsibilities besides being the primary person who does the agriculture. It promotes sustainable farming practices, right, that protects the environment. Innovative solutions such as agroecology and precision agriculture can improve food systems. What I have found in my own interactions with number of farmers across number of countries is that they are very progressive and they know a lot more than we think they know. I'll give you an example. I was in Colombia, in rural part of Colombia. It was so rural that we had to stay at a farmer's house. Farmer and 2,000 acres of land around the farmer's house. As far as I could see, I could only see his cattle. There was no electricity. And there was one solar panel that provided, that powered one light bulb in each of the rooms. And there was a generator that was turned on only when cell phones needed to be charged. So few minutes every day. And the primary source of news was a radio. I stayed at the farmer's house for 3 days. We were doing some work, developing, talking about how that whole region needed to be developed and what could be done. And there was a language barrier. You know, the farmer and his wife only spoke Spanish. I could speak only English, but we were able to talk through an interpreter. And I asked him, you know, what are the challenges that he has? And what he described to me is what state-of-the-art climate change models are telling us. And this guy had probably no idea about any of the CMIPs and any of the climate models, but he said, sun is getting hotter. The water in the ponds are drying up. Groundwater is going down. I'm worried about my cattle. My cattle, because of the sun is getting higher, is hotter, is producing less milk, and then cattle that are used for meat are growing less healthy. And I was totally loss of words, you know, how beautifully he described what our climate models are telling us what's happening. And so I asked him, so what are you doing? And he said that he is thinking about putting a number of solar or wind-powered pumps at different places along his farm to help his cattle and wildlife, because wildlife also needs water to survive, and they are important to maintain the ecosystem in his 2,000 acres of land. So there was someone with no knowledge of ecohydrology and no knowledge of ecosystem services was thinking about what we are talking here, right? So next time when you talk to a farmer, find out, ask them rather than unloading your knowledge to them. Clean water and sanitation, goal number 6. When you look at child mortality between 0 to 5, water is number 1 cause. And when you look at the stunted growth and why children in many parts of the world do not attain a normal adulthood, the reason may be water. The objective here is to improve water quality, increase water use efficiency, and implement integrated water resource management that we have been talking about, and improve water use efficiency along all sectors, right? So, number 1 user of freshwater withdrawal globally is agriculture, and that goes to produce food. 20% of world's agriculture is irrigated. So irrigation is absolutely needed, otherwise we won't have food security. And the risk will be too much if it is not irrigated agriculture. So idea is not to take the water away from irrigation that is so vital to production of food. Idea is how can we make it more efficient by looking at improvements in water, improvements in plants, and improvements in technology, and that's where you come into picture. That's where you can make a difference. And how can we implement integrated water resources management at all levels? And then how can we seek to protect and restore water-related ecosystems, right? So take a look at this in depth when you get a chance. The climate action, goal 13. Climate change is happening, it is real. what can we do to not only mitigate it, but what can we do to adapt and build resilience, right? In Connecticut, where I live, a lot of our focus is now gone into building resilience. And what can we do to protect the communities that are vulnerable? The impact of climate change would not be shared equally across all segments of the society. Those who are poor will suffer the most. What can we do to minimize the impact on them? And in Connecticut, we are doing a lot of work along those areas, as well as what can we do to adapt to the climate change that is already happening. So the models we have been talking about, eco-hydrological modeling, it plays a vital role in climate action. You saw some case studies that Professor Vamsi presented. Adaptation strategies aim to enhance carbon sequestration, reduce greenhouse gas emissions, and preserve biodiversity. 2 years ago in Connecticut, we produced a lot of specialty crops. We produced a lot of fruits. And there was an early onset of warm weather in February. The apple and peach trees blossomed. And then that followed with the frost, killed all the flowers, and practically eliminated all the apples and all the peach that year. Who was impacted? It was the farmer who was impacted, who was relying on that income to carry the family, through the next year. The wealthy could go and buy apples and peaches that came from other states, from a grocery store. And those are the kind of challenges we are going to face more and more in future, right? So you can come and be helpful in developing strategies that can help our stakeholders adapt to climate changes. Life on land aims to protect, restore, and promote sustainable use of terrestrial ecosystems. How do we manage forests sustainably, combat desertification, and halt and reverse land degradation and biodiversity loss by 2030? 2030 is what, only 5 years away? Preserving natural habitats and restoring ecosystems, and enhancing biodiversity, improve carbon storage, and provide vital ecosystem services. Do you all feel like you're getting tools in your toolkit to be able to address some of these things? You may not be expert right now, but at least we are orienting you in the right direction, right? That if you keep going, you will become real experts, and you can really contribute to some of these goals. So on the water scarcity, it represents a critical challenge to sustainability that is intensified by climate change, rapid population growth, and inefficient water management practices, and challenges in food production and economic stability. The climate change, extreme weather events such as hurricanes, floods, seems like it's happening a lot, and it's happening at a lot bigger magnitude than what it used to be. And it's disrupting the delicate balance of ecosystems, making it difficult for species to adapt or migrate to suitable habitats. So, what's happening in India? You all should be expert. You all live here, right? You all are familiar with the literature. But you look at any period and you see the warming climate, 1911 to 1961 to 70, and then 2011 to 2020. January, February, warming, right? March, April, May. Significant warming. As a child, I used to remember that, Holi was the first time when you start to feel the warmth. And now it is much sooner than July, August, September, much warmer, and then October through December is also 1.6 degree warmer than what it was at the beginning of 20th century. And so clearly the climate is warming in India, and what that does, it puts a adverse impact on water, it puts adverse impact on ecosystem, on food production, on health, everything. One of the biggest concerns we have, one of the departments in my college under me is Department of Kinesiology. And among different things that Department of Kinesiology does, one is looking at heat stress and impact of heat stress on humans. We have one of the leading experts in the world who does that research. And when I talk to him, he tells me that one of the biggest concerns he has is how do we ensure safety of agricultural workers who are working in hot climate that could be deadly moving forward, and what policies are needed to ensure their safety. See that with the warming climate. On land use challenges, of course, increasing population, and that is driving the urbanization, is putting a big pressure on land use and land management. And along with that, the soil degradation that is happening in tropics, that is altering the hydrologic response. Surface detention and infiltration are reduced because of land use changes, and that is reducing the groundwater recharge, that is increasing the surface runoff. So what happens during the low flow conditions, the dry season, rivers are running dry. And because it affects the groundwater recharge and soil water content, thus reducing the feedback that goes back to the to atmosphere. And so solutions to zero hunger, approaches such as agroecology, permaculture, where we are prioritizing ecological health while enhancing food security. And agroecology encourages the use of organic farming techniques, crop rotation, and incorporation of native species which are more adapted to the changing climate, right, which can be drought resistant, which might require less input as in water and fertilizer. And then permaculture practices, they focus on designing agricultural landscapes that mimic natural landscapes. And we need collaborative efforts, including government policies and community engagement, that are essential to bring these solutions to scale. On solutions to clean water and sanitation, of course, integrated water resource management and public education and community participation are essential components of IWRM. One of the things that we do when I was at Purdue was in our surrounding watersheds and streams, we will bring the community together, and we will do the water quality analysis of rivers and streams in the surrounding areas. So everyone will go out, everyone will be given a protocol and a water bottle to go and sample the water, bring it back, and we had quick tests to analyze the water quality. And it was a community science, citizen science, where we were engaging the citizens to do the science with us. And it was one way to increase the awareness of what is happening in your backyard. And what can you tell about the quality of the water? We have published some papers on that. Rebecca Laxton published a paper related to that citizen science that we do. But it was a great way to increase awareness of our actions impact the quality of water in your backyard. I don't know the numbers for India, and I don't know if those numbers exist or not, but in US, everyone lives within 10 miles of a polluted water body. Everyone. And some of those things were very visual. You know, when you go, you step into a stream, collect water sample, bring it back, we analyze it, and we share the results. And so when some of you get into a position where you can do the citizen science, think about it. Think about what you can do. On climate action, this is such a big and complex problem, but we need to think about all three components: mitigation, adaptation, and resilience, right? Mitigation in terms of what can we do to reduce the emissions. And then what can we do to invest in climate resilient infrastructure such as flood defenses and drought resistant agricultural practices. Doing research on what are some of the crops that are tolerant to heat and moisture stress, as well as nutrient stress, and promoting those practices. Education and capacity building, programs that can equip communities with the knowledge and skills that are needed to adapt to changing climate conditions. And adapting international cooperation and sharing best practices can accelerate the implementation of effective climate policies. Life on land, habitat protection, restoration of degraded lands, promotion of, I feel like there is a lot happening in restoration of degraded lands here, right? Is that a correct perception? When I talk to folks, I really get that perception. Promotion of sustainable land use practices that balance human needs with environmental health, and restoring ecosystems such as forests and wetlands. Implementing agroforestry and permaculture can help maintain biodiversity while ensuring food security. And communities that do that are, what you will find, that are the communities that are the healthiest and the happiest and usually the most affluent. So it helps everyone. So where does SWOT model fit into all this? It can play a role, and it is playing a big role in evaluating different practices, in informing the science, in informing the policies. Professor Vamsi presented 17 different scenarios that we had analyzed with respect to bioenergy production and how that impacts energy versus food. And there was a big debate going on at that time, food versus fuel. And we were able to show that, yes, there will be some decrease, but that decrease will necessarily come from areas that should not be under food production to begin with. And if we put those areas under energy production, we can meet both goals. Those are the kind of things that SWOT model can provide to you. It can simulate the impact of agricultural practices on agricultural productivity, soil health, and biodiversity. And it can also be used to simulate how various mitigation and adaptation strategies affect water resources under climate change. We looked at some of the emission scenarios and how that affects bioenergy production. And then it can be used to evaluate the impact of extreme weather, such as floods or droughts, and water availability and crop yields and food production, and can be used to simulate a variety of best management practices, such as contour farming, no-till farming, cover cropping, vegetated filter strips, wetlands, you name it. There are a range of BMPs that can be very effectively simulated in SWOT model. So it gives you a powerful tool to be able to go and look at what may be happening in a watershed, what needs to be happening in a watershed in linkage to sustainable development goals. So, case study, flood challenges in Jakarta, Indonesia, because of the climate change, because of the population density. It's a huge problem, so much so that Indonesia is going to move its capital from Jakarta to somewhere else. And this move aligns with international framework like Sendai framework and disaster risk reduction, because if they don't do that, then the cost of recovery from flooding will be too much for the country to bear. And this should be the last solution, right? That you develop the area to the extent that now it's hard to go back, and you have completely tilted the balance. Now, case study 2, use of SWOT model to evaluate the effect of agricultural BMPs. Bhavesh, right? Bhavesh, where is Bhavesh? You want to present? Come on over. Don't look at him. Come on over. At least both of us can present it. So come. Folks, a big round of applause for Bhavesh.
So my friends did this work as a part of my MTech work under Professor Vamsi Krishna. So here we are consider basically three type of structural BMPs, not the non-structural like what Sir Professor Chavez had told. So we are consider this check dams, ponds, and bund and terraces. Okay, 4 structural BMPs to reduce the sediment retention or sediment flow out from the Suvarnarekha river basin, and we try to put BMPs in each and every individual subcatchments or subwatersheds. The subwatershed size, if you see, it is more or less 50 km square. Because if you put any type of structural BMPs in a huge watershed or subwatershed, it will not give satisfactory results. It will be good for the lower order stream, or you can trap the generation of the and transportation of the sediment flow out from the stream. So the basic hypothesis here is, if you go to SWOT model, there is a option under BMPs called pond parameter you can put there. There is no function to put the check dams, but might be SWOT plus have these options now. So there you can put what could be your size of the check dam in terms of length, depth and storage, and what could be the inflow and outflow, everything. So check dam as well as pond are simulated in the same way at the outlet of the any particular stream or any particular subcatchment or subwatersheds. But in case of terraces, terrace basically reduce the slope approximately 0, because it is like staircases. But in case of bund, it will just reduce the slope length, not the slope value. So in case of terraces, we give approximately very less value, slope length approximately near to 0. And in case of bund, we reduce the slope length only. So there is a parameter in the sort also. You can change the slope length and the slope values. So after that we simulate as well, like from 30-year simulation and 10-year validation, and this is our basin, basically Suvarnarekha basin, which is covering this Jharkhand, Bengal and Odisha, some part of Odisha. Okay, and it is basically we find out that at the time of field survey there is a lots of erosion due to improper knowledge in the management practices. So this is the basically scenario we are formed. First scenario, we are going to this is as a normal condition. There is no check dam, no bund, no structural practices, nothing. So coming to the second scenario, first scenario we told, which is watershed with only check dams. We put numbers of check dam in the outlet of each and every subbasins, only check dams. Then it's coming to only farm ponds. Then we put bundes and terraces. Then we find out which watersheds are prone to erosion based on the statistical analysis and USLE methods, which already SOIT have USLE. You can otherwise you can use GIS data to calculate the USLE soil erosion, annual average soil erosion. So based on that, we find out top 75 sub-watershed which are more erosion prone and put there the check dam of farm ponds. Then like that 50 and 25. Then compare the results with baseline scenario. The scenario we are making, because if you going for only check dams, it is taking much more money economic point of view. So why not we are combine the conservation practices. In order to put only check dams, we put this bund and terraces, because for bund and terraces the excavation cost only there. So concreting unit required to done. So this is the improvement, basically baseline minus scenario by baseline normal equation. So if you see, these are the reduction of the sediment concentration under various scenarios. Okay, so scenario 4, if you see, 40% reduction is there. Okay, and scenario 4 means watershed with all soil and water conservation practices. Like each and every watershed, we put check dam, farm pond and terrace, everything. But in case of scenario 4, if you see, scenario 7, 34. So 54 is highest if we consider all type of conservation practices, and if you consider only 25% of them in the first order stream, then it will give 34%. Now it is your decision as a decision maker, which one you want to choose, depends on your capital, like land level capital. So these are the results which are plotted here, and as SOIT basically working based on this water balance. So balance component of the subbasins are presented for each and under scenario here. So that's we mention here, like 45% reduction can be possible if we put all this check dam or farm pond or terraces in each and every watersheds. But it is again your decision which one you want to choose.
That was the last slide.
Okay, sorry.
Okay, thank you. You did a great job without knowing what the slides were going to be like. Well, Bhavesh didn't know that I will call him to make a presentation. His advisor did not know that I will call him to make the presentation. Bhavesh, great job. So, what do you get out of this case study? 44% of the areas have severe erosion in the watershed, right? And that means that nearly half of the watershed is having significant soil losses, and nearly half of the watershed is going to be contributing significantly to not only soil health but also water quality problem. And three simple solutions is what he looked at, and where those need to be put, right? So when you look at, when you are putting all three solutions in the watershed everywhere, right, how much is the reduction that is happening in the sediment yield? About 47–48%. But even if you don't do that and apply those BMPs to only half of the locations, not at every location, but only half of the locations, you still get a significant reduction right here in scenario 6. And if the resources are not there, and you could go and do it only in 1/4 of the locations, still the reduction will be remarkable, 40% reduction. And that will play a huge role in maintaining the soil quality, in maintaining the soil health, improving the water quality, and improving agricultural production, because you are putting the fertile soils at their, keeping the fertile soils at their place. And so that's the power of BMPs. What this does not talk about is how you can optimize it, right? So when resources are limited, and when you have only a limited amount of money and you have to pick and choose, how do you optimize it? There are a number of papers and work that has been done to do this spatial optimization, including some of the work that has come from my group, and you can look at it. But even if you don't have computing resources to optimize BMPs, you just do some simple assessment of where are the vulnerable areas and randomly pick 25% of those areas, you can improve the health of your watershed drastically. And that's the take-home message I want you to take back, that these BMPs, these conservation practices, are very powerful tool to improve hydrology, water quality, and enhance the food production. So they meet multiple goals. And this is all done using the SWOT model. So that's where you can bring a model like SWOT or any other watershed scale model that you may be working with, and then link those results to sustainable development goals that we are talking about today. So with that, questions? Yeah.
I have two questions related to this case. Question is, while the scenario 2 and 3, when watershed is constructed with check dams and farm ponds, so which stream order is considered for this development?
So these are usually the first order streams where the check dams, and it's hard to do that in anything bigger than that. That is correct, right? This is all done in the first order streams. Yeah.
Yeah, and my second question is, sir, while we give any means proposals like these are the places where the check dams and ponds are constructions, you also consider the return period and the discharge also. So will this mean things are considered, like if we proposed that check dam should be constructed, so and for extreme events also, so what should be the means period so that the ponds or dam is resilient to means the.
So I see you're asking about how do you bring the climate change scenarios into the evaluation of what should be the size of,
Yes,
of
sir.
farms and
Like we propose, sir, for like
Yeah.
there should be the discharge based on this discharge.
Yeah.
What should be the means?
Yeah, so I don't believe that this case study includes
Yeah.
climate change scenarios, but this study does include the weather and climate data that goes as an input to the SWOT model. You can bring any of the emission scenarios to then do the analysis. Either the baseline analysis in a way that under current precipitation scenario, when you are designing the check dams and ponds, are they going to be adequate if you bring the climate change into analysis? Or you can bring the climate change data and say that what should be the size of those. So either one of those two could be done. But also, Vamsi, you have done some work on how this could be used to supply irrigation water in surrounding areas, right? And an amount of irrigated land can be increased significantly. So it's not just improving the erosion, but it's also providing you water that can be used during dry periods to apply irrigation in the surrounding areas. And that was quite significant, as I remember from one of your publications.
Yes, sir. There was an increase of 150% in the area, in the irrigated area. So you have a check dam, you have a pond, and then you supply it to the nearby area. Usually supply it in terms of, so we considered only the irrigation part of it. So when you have this, you can optimize it, optimize the site. As you said, the optimized site has to be optimized to meet upstream and downstream requirements, and then we started supplying. And then one of the case studies that we have taken was can we apply a dip irrigation schedule. Now when you apply this dip irrigation schedule, it will increase the area that can be applied. Now there was a challenge in this irrigation schedule. This is a small structure. If you leave it out for too long, it will evaporate. And if you apply early, the crop will not get realized. That's the optimization problem that we were able to take up. And that increased the yield to almost 50%. The area increased by 150%, the yield increased by 50%.
Yeah.
Of production and that was a simulation optimization framework.
Yeah. So these are the kind of powerful analysis you can really do. And these analysis can make a big impact in the water sets that you are working in.
So, when we are assessing the vulnerability of an area to a particular event, let it be a storm, let it be flood, whatever. So, usually the hydrological sensitivity might not coincide with the economical sensitivity. So, there could be economically weaker sections in these areas. So, how can we integrate that into the vulnerability analysis?
So there are two components of economical sensitivity. One is how much resources do you have to make these improvements and implement these BMPs. And it becomes a conflicting objective function that more you implement these BMPs, more expensive it becomes, right? So you can optimize it in a way that you are achieving your environmental goal, let's say 40% reduction in sediment losses from the watershed, while not exceeding certain amount of dollar value that it will cost to implement those BMPs. And we didn't talk about optimization, but there are lots of papers, work by Professor Vamsi, work by Sibin Raj and Chetan Maringanti. Look at, they have developed methods to optimize BMPs in a watershed. It's computationally very complex. So if you get into that, it's a very exciting field to work in, but you have to realize that you need adequate computational resources to be able to do that. Vamsi, you were running it on Purdue supercomputers, right? So that's the kind of thing you would need. Other one is who is benefiting, right? And so bringing that, so that becomes a special optimization problem, that if their fields or their locations are in certain part of the watershed, and you need to make sure that those get selected, those don't get omitted as a selection process, then that needs to either come as an objective function or needs to come as a constant, that these areas, whatever you select, these areas must be selected, and that will be one way to ensure that.
I have to ensure that make that as a special objective to go with the.
Yeah.
Sir, related to water scarcity, the water stress is due to the water availability. Stresses are due to the consumption of water availability. what does exactly water availability means? Like Rajasthan is having very high water stress due to less water availability. So my question is, what exactly water availability defines?
So, I'm trying to understand your question, but generally speaking, to me, the water availability is the function of two things: water quantity and water quality. Right? So, for the purpose for which you need water, do you have enough water and is it high enough in quality? So, if we, let's say the drinking water as an extreme example, right, because it is the highest quality water. You may have water, but if it is not sufficient quality, if it is not potable, then your water availability is very less or zero. And for other purposes, such as irrigation, if it is reclaimed water coming from wastewater treatment plants, and you have taken out the heavy metals and you have taken out pathogens that otherwise may get into a fresh produce, then it may be high enough, right, the quality may be high enough to be used for irrigation purposes. And so the water availability may be higher compared to if you are strictly looking at the drinking water. Or if it is for an industrial purpose, it may even be a lower quality water because you don't need to take out all the elements that otherwise would be needed to be taken out for irrigation or for drinking water. So the water availability has these two components. It's also, there is a temporal component of that, right? If you look at global water distribution and when water scarcity becomes a problem, usually during the summer periods when it starts raining, less water is available, and both quantity and quality. In many parts of the world, folks have to travel many kilometers to go and fetch water to drink for their everyday domestic use. So that's what I mean here. Yes.
Like you said, people have to be more science in that everyone has to go and collect water like that. So in India, the government will mark hand pumps if they are giving toxic water, but they will not provide alternatives. So people are forced to use that only. So what happens in US when they found out that streams near them are polluted?
So a number of things happens, right? Well, let me put some context behind it. If you look at the streams and rivers and lakes are really well monitored in the US. It is something that is done really well. And every 2 years, there is a report that Environmental Protection Agency produces. That is the 305B. So that is the 305B is the rule under which this report needs to be published. And so therefore the title of the report is 305B report. It's the status of the water resources in the US. You can go and download 305B reports. These are publicly available. Within that, there is a section called 303B, 303B. And that is the list of impaired water bodies that are impaired for any purpose, for any constitutional. So if the purpose of a river is to supply water for industrial use, and it is not meeting that industrial use standard, then it will go in the 303D list of impaired water bodies. So not everything is from the drinking water point, because you don't go to a pond and drink from there, right? So it's not fair to evaluate everything from drinking water quality standards. So how it is evaluated is what is the intended use. Are you going to swim in that pond? And if you are going to swim in that pond, then is it meeting the swimming standards which are separate from the drinking water standards? So it is use specific. And then that's where the role of us scientists come in terms of what can we do to develop watershed management strategies to improve the quality of the water. And what kind of BMPs can be put in place? What kind of educational programs can be put in place? How can we work with farmers and other stakeholders to roll out initiatives to implement those BMPs, implement educational programs to improve the quality of the water. And a lot of money goes into that.
Related to that only, you said, as you have previously said, we are getting the idea that US has very structured things. If we are going to implement the same structure in India, is it only the policymakers who are doing this, or what is the role? We can force a scientific company to go for the structured way.
So I can't stand here and tell you what India should do. That's not my job, and that's not my role, right? And I want to step out of my sphere of influence.
No, not in India.
But so there are, if you look at the non-point source pollution programs in the US, much of it is voluntary. It's not regulated. Point sources are regulated, non-point sources are not. And that's where lots of education come into place. Lots of universities working closely with farmers and communities and stakeholders come into play, where we are actively taking the research that happens, translating that into actionable items, working with the communities to implement those strategies. So rainwater harvesting is one of those things which is very popular here. It's an example of how you can bring the research into an action and get that implemented at the community level. Other one is when a new subdivision, when a new neighborhood is developed, there's lots of hydrologic assessment that happens to look at how much more runoff will be generated and what size of retention pond do you need. And then what can be done with that retention pond. It becomes a part of a landscape where that retention pond is designed because hydrologic assessment is done before and after. And then looking at how the lawns need to be managed so that there's not a whole lot of nutrients running into the pond and soaking the pond with algae that blooms. So that's where the power of working together between the universities and communities come into play. I see that a lot. I work the extension is part of my college. It's a learning. And we have extension programs in each one of 169 cities and towns in the state of Connecticut. Connecticut is a small state, and it consists of 169 different sized cities and towns. We have our extension faculty working in each one of those. We have at any given time 500 different projects that are happening where they are working hand in hand with municipalities, with individuals, with the communities to translate the science into actionable items. And that makes a big difference. And those people are everywhere. It's not just the Indian context, you know. Any society you go, and there are three types of, broadly speaking, very oversimplification. Those who are early adopters, you know, who would adopt the practice fairly quickly. And those who would never adopt it, no matter how much you are convincing you are going to do, they know they are right, and you can't convince them enough. And then there are people, probably 60 to 70% in the middle, who are waiting to see is it going to work or not work, and that they can be influenced. So one way extension does is working with the early adopters to adopt these practices and then use them to influence their peers. And this is what I'm doing, demonstrating this is the impact it is making. And if you do this, this is the benefit you will get. And so that is one of the strategies that are implemented to identify, build a relationship with early adopters, bring them on board, and use them to influence their peers. Okay. Thank you.
Before we go for a short break and have a small validatory function, we have the feedback forms which Gian wants to give. Obviously, we'll take your feedback, but in the meantime, can you
So welcome back everyone to the valedictory function of our 5-day Gian course on eco-hydrological modeling organized by the Department of Civil Engineering, NIT Warangal. I request our dignitaries to come to the dais. We have Professor Venkat Reddy, Head of the Department Civil Engineering. So please take your seat to the dais. We have Professor Indrajit Chaube, experts for the course, and our course coordinator, Dr. Vamshi Krishna. I now request our head of the department to felicitate Professor Chaube with a memento. I now request Professor Chaube to share his experience.
Thank you very much, Asi, and thank you very much, Professor Reddy, for the warm facilitation. It has been tremendous experience being here for the last 5 days with all of you. And so I want to congratulate all the participants first for taking an initiative, enrolling in this workshop, and being with us for 5 days. Give yourself a round of applause. many months ago when Professor Vamsi approached me and asked about the idea of writing this proposal together and teaching this Gian course, the decision on my part was easy. I had heard a lot about NIT Warangal. I had very positive impression from those who knew the place, who I had interacted with. So I wanted to come and I wanted to experience the beautiful NIT Warangal. And I said, yes, let's write the proposal together. We wrote and it got funded. And I got very excited with the prospect that, okay, I'm going to go and spend a week at NIT. Then the real work started for us to start thinking about how we wanted to design this workshop, what will be most meaningful to the students, and what should be the content that every participant gets some new information out of it. And what ensued for last 2 months is a meeting every weekend we had with Professor Vamsi and Asi to talk about and preparing for this workshop. And you have no idea how much work they have put into it and how much has gone into preparing all the materials, all the lecture notes, thinking about the design of the class. So I want to sincerely thank Professor Vamsi, and I want to sincerely thank Asi for I know this is an experience that will help you a lot grow professionally and do well in your career. Also, Professor Vamsi has been an incredible host. I have enjoyed every moment of being here. And we have talked about furthering this collaboration. The timing could not be any better between the two countries, India and US, with new government coming there. Already the relationship between US and India is the strongest it has ever been, and I believe that it's going to be even stronger moving forward. And what I believe that there will be many opportunities to start bilateral projects, and I'm looking forward to being a part of some of those bilateral projects where we bring University of Connecticut and NIT Warangal together, and we bring our faculty together to work on issues and challenges that are in front of both countries, and putting our collective brain power together to find solutions to some of those complex problems. It has been an absolute joy being a part of the Gian course, and once again, a very sincere thank you, Professor Vamsi. Very sincere thank you, Professor Eddy, for warm hospitality and making this meaningful to all students and making it truly memorable for me. Thank you.
Thank you, sir. So we can have feedback from the participants. So please come over here and share your experience about the course.
Good morning, everyone, and I am very blessed to hear today to share my experience in last 5 days. It's my first Gyan course, and it was I think will be a great learning for our life and research field also. I am from IIT Indore, and I am doing my research just started in January on climate change assessment for Narmada River Basin. So the BMP practices and the ecosystem services and the eco-hydrological concepts I will be I think now I can be clear about those things and can be implemented in my work. I will ensure to my supervisor to take this kind of activities for our research works and create some workshop and awareness for these things to our societies, people who are just only taking services from the ecosystem and nothing doing for them well-beingness and their health. Such kind of rivers and ponds are getting so dirty and out of running out of water kind of things is happening nowadays. These experts are here. So I am blessed, sir. Thank you for you people. Thank you, sir. It's just a great journey. Thank you, sir. Thank you.
Thank you. Anyone else?
Hello, my name is Aradhna Shukla and I'm a first year MTech student in water resource engineering at NIT Warangal, and I am very new to this, so I am still exploring a lot of things. I have not done research or anything, but this course was designed in such a way that I was able to understand and grasp the concept and all that thing. And it is very interesting how a lot of practical things have been taught in this. So I'm glad I attended this. Thank you so much.
Yeah. First, thank you to the Gian program, NIT Warangal, arranging such good hospitality and conducting this course. Many congratulations goes to our professor Vamsi Krishna Vema and our international faculty, Professor Indrajit Chaube. So the course was well designed and well structured. This, which is the most important, I as a researcher considers, because as I hope that everyone came here as a participant, we all came as a new entrant to this eco-hydrological modeling, where we have not much background on the eco-hydrology. The structure of this course was amazing, that we have get to know all the basics and the fundamentals of the eco-hydrological modeling. When we approach the eco-hydrological problems in future in our research, I hope these basics would help go in a proper direction. So, and the faculties also, this Professor Chaube and Professor Vamsi Krishna Verma have delivered in a very nice way, so that we could not able to deviate from our research aspects. So that way, and particularly to the hands-on session. So we are will be jumbled here and there in any of the courses that we attend outside, but here the hands-on covers in a proper way, and it completes its entire outcome, its expected outcome. So I thank both of the professors from the bottom of my heart, and NIT Warangal is such a nice place, and its warm welcome and hospitality has been appreciable. Thank you, sir.
Good afternoon, everybody. I'm really thankful to Vamshi sir and Indrajit sir for giving us such an enriching and enlightening session on eco-hydrological modeling. So when I am actually from civil engineering water resources. So right now I'm doing research on hydrological modeling, and this is a new concept for me. So, I'm happy that I learned so many basics on ecology, hydrology, and even also today what Indrajit sir was discussing about citizen science, which, I want to explore more. So, and also I'm, appreciating the efforts taken by the coordinators. Thank you. Thank you.
Good morning, everyone. Good morning, sir. First of all, I would like to say thank you very much, Professor Vampi Krishna sir and Indrajit Chowdhury sir. Currently, I am a research scientist at NRSC. Now I am going to set up a 19 model setups, including calibrations. This makes me very comfortable to do all the model setups. And I thank Mohammad Rafi and Asi and so many MTech scholars also like Vaishnavi and Manoj and Lokesh. Those helped us in hands-on sessions. And not only to the GAN program, I'm very happy to connect with many people like a VIT person I have and Babesh and all. They suggested me some of the courses what they offer in IITs and VITs. So thank you all and thank you GAN. Thank you sir.
Anyone else? Yes.
First of all, thank you very much, NIT Warangal. Thank you, Indrajit Chaubey sir. Thank you, Vema sir. Sometimes life takes very unexpected turns. So after 1.5 years, I feel that I again came to Adobe. So I left academics and not left the science. So such kind of the course are very essentials for the for us to grow in our futures or to grow in our professional schemes. So it's very honor for me also, and it's very honor for you also that you are participate in this course. And I hope whenever you go or whenever you try something hands-on, the actual realities, so you use this kind of the course or this course for your future endeavor. Thank you very much.
So thank you all for sharing your feedback. So feedback is important because there is always a scope of improvement. So even I would like to share my personal feedback. So it was learning in multiple aspects in terms of helping in creating the content. Obviously, there were many MTech students, Rafi, Indu, who were constantly helping in preparing various aspects of this Gyan course. Also, throughout the course, we had many technical addition to our knowledge, what we know and what way we can improve. Since I have completed 2.5 years, so I'm somewhere in between my research journey. So still there is a lot of scope of addition of concepts of eco-hydrology. And then there are other aspects of learning when we see our teachers teaching us that how what all we can improve in our delivery and how we can also improve our personality in terms of entering into the professional field. So thank you all for providing this platform. So now moving forward, we can continue with the certificate distribution. I would like to request Professor Chaubey for distributing the certificates. So Abhishek Rai Singhani, Aishwarya SL, Anish Chandra, Anjana M, Ankit, Aradhna Shukla, Bhavesh Das, भूपेंद्र कुमार, सत्यराज, गिरीश, साहिती, खुशहाली, खुशबू, पवन, मंजुनाथ, साई भरत, मधुर, नवीन, निल्जा, मेखला, मेखला, पट्टाभिरामन, पूजा, पूजा SN, पूजा के, राकेश, साई दत्त, राकेश, शाइनी, श्वेता, कीर्ति, श्याम, विनीत कुमार, तृप्तिमय, नीरजाक्षी, विनोद, श्रव्य, यशवंत, अरुण, अरुण, मनोज, Vaishnavi, Lokesh, Rafi, Now I request Dr. Vamshi to present vote of thanks.
Good morning, everyone. Right. So, at the outset, I would like to thank the Gian program, Ministry of Education, for facilitating this, for funding this course. And Professor Chaube, when I sent out an email saying that this is an opportunity, can we try? And he was straight away said yes. He said, let's do it. And from then on, after the approval, it was, as he said, lot of work has gone to create this. And from the institute side, I would like to thank Professor Venkat Reddy, head of the department, for encouraging to participate and organize these kind of programs, institute administration, the director and deans for smooth facilitation. And my research team, Ashi in particular, and when we and Professor Chaube were discussing what kind of course content, what is to be prepared, and what kind of lecture notes to be given. So first thing I searched was, is there any book that is available that I can directly refer? Can it be directly given to the participants? Then we realized that there is no book that is available. So everything had to be prepared from the scratch. And that is where his inputs, and we brought in Ashi, who has done a lot of work over the last 4 months to bring that 130-page book, which is in itself is a big achievement, which I feel, right? And that book was a comprehensive from the starting to ending, and it took a lot of planning, lot of inputs from Professor Chaube. Every weekend, 1 hour we were meeting to discuss each and every step, and that has brought into this particular course, right? And that is where usually it's a longer course, it's a semester long course if you want to expand it and bring out all, but when you want to compress it into 5 days, you wanted to make sure that the key information gets through, and the remaining things can be a point where you can go back and learn, right? So thank you, Ashi. And as said, organizing this particular course requires a lot of background work, and that is where my research group has helped. Rafi, Arun, Lokesh, Manoj, Vaishnavi, Indu, they all have been incredible support, and without their support it would have been far more difficult to do this. And so thank you to all of you, and thank you to all the participants. I saw the feedback. In general, it's all good, right? And everyone said it's a good course, and hands-on session can be improved. Yes, can be improved. We will take it in our next one. And someone said mosquitoes, but yeah, this is a good time. This is a good weather, right? It was a very pleasant weather these 5 days in Warangal, which I liked. That's 24-25 degrees, but that's also a good time for the mosquitoes. So in that sense, it did not work out. But yeah, in the summer it's too hot, but mosquitoes will not be there. And the previous week, the week before this course, it was slightly more cold than here, right? Anyway, so hope you all had a good time, good 5 days, and you take home with some memories and some knowledge when you go back to your institutes or when you go back to your work. Okay. Thank you for being here. Thank you, sir, for coming all the way for 5 days, which is probably the first time you have done. We were talking about it. So it's a lot of commitment. 5 days, being a dean of university and coming here and spending 5 days is a lot of commitment, and that commitment was also the previous 3 months, where every weekend we had a meeting and he made sure that he was there. And thank you, sir, for it was a nice interaction for 5 days. I could learn a lot, even though we have been interacting for last 10 years. But these 5 days were had a different idea to different segments. Thank you for being here. Okay.
So in yesterday class we have set up the model and we plotted this hydrograph. Okay, what we observed here, it is, so here the blue one is indicating simulated flow, right? And this orange one is indicating observed flow. So here we can clearly observe that simulated was very high compared to observed flow. So our model was overprotective. Okay, it was not, it was overprotecting the actual flow. So what we need to do, we need to adjust the parameters in such a way that it should be able to capture the observed flow, right? So to fine tune those parameters until it reaches the best match with the observed flow, that whole process is nothing but calibration. Okay, that's what we are going to do now. Okay, after that, so before we are going to perform calibration, we need to divide the entire data set into 2 data sets. For example, we have run the model from 1990 to 2010, right? Or a whole, some people run for the whole period. So we need to divide the entire full period into 2 data sets. One for calibration, one for validation. Validation is nothing but what? We need to cross-check the calibrated parameters with an independent data, so that we will get to know these calibrated parameters are fitting for the other period or not. Okay, that is what validation. If they are able to capture observed stream flow perfectly in the validation period, that means that whatever the parameters we got through calibration, that is perfect for our watershed. So we can use those parameters for the predicting future flows. Okay, understood? So before going to do validation, first we need to do the calibration and find out the calibrated parameters. Okay, so now we will divide entire data into 2 data sets, 1992, 2010, right? Actually, it will take time to run the model. Like in the SWAT-cup, we need to keep some simulation, so it will take time. So as the time is not that much there, so we are just doing some 5 years calibration, from 3 years for validation. Okay. Now for this class we will do 5 years calibration. Means we have given 3 years homework period also, right? So our results were there from 1993 to 2010. So first 5 years will take for validation. The remaining 3 years will take for next 3 years will take for validation. So 1993, 1994, 1996, 1997. So these 5 years will take for calibration. We'll do calibration for these 5 years. Then we'll test those calibrated parameters for the remaining 3 years. Okay, 1998, 1999, and 2000. Okay. So for that, we have one software called SWAT-cup. Okay, to do this calibration. We can do it in externally also using some algorithms like amalgam or some genetic algorithms. So we can use that also. But this SWAT-cup was developed to do all this calibration smoothly without doing in any other external coding, everything. So they kept everything. So just we need to give the data. So that inside there is an algorithm called SOFI2 or some other algorithms are there. So we have to choose one of the algorithm to perform the calibration. Okay. All of you open SWAT. So one more important thing. When you are splitting the data into two different data sets, one for calibration, one for validation, you need to split the data in such a way that those two data sets should be similar, statistically similar. As Sir told in the lecture also, right? Calibration period and validation period data should be statistically similar. Mean and standard deviation of calibration period, mean and standard deviation of validation period should be similar, so that whatever the calibrated parameters, it will fit automatically with the validated periods. For example, suppose you have divided the data into 70-30%. There is no rule in hydrological models, physics-based hydrological model. There is no rule that we have to take 70% data for calibration, 30% data for validation. When we are doing for machine learning models, that is with there 60%, 40%, 70%, 30%. When we are doing these hydrological models, there is no rule that we have to take 70%, 30%. Okay, we have to divide the data into two different data sets. Those should have statistically similar, in such a way that you need to divide. Otherwise, what will happen? Some days more flow will be there. For example, in the validation period, more flow will be there. In the calibration period, the flow was normal. So whatever the parameters you have fitted in the calibration period, those parameters were not able to capture this high flows in the validation period. Okay. So again you need to come back and again you need to do calibration. Okay, calibration is not a 1 day, 2 day process. It will take some time. 15 days it will take. 20 days it will take. So when dividing the calibration validation period, we should divide in such a way that the both data should have similarly, statistically similar. You just keep this in mind. Otherwise, we will do calibration because this is what I have faced during my learning. I divided the data into simple 70%, 30%. So in my validation period, I have some high flows. So whatever I have done 1 month of the calibration period, which is with those parameters are not able to capture the validation period. So again I divide the data into statistically similar, then it was successful. So keep in that mind that you should be dividing the data in such a way that those are statistically similar. Otherwise it will take time. Okay. So now, as of now, we are not doing that, but when you are doing for your watershed in your research, how to take care of that. Okay. Now first we will take 5 years for the calibration. Okay. This is SWAT curve interface. Okay. What is the input for this SWAT curve? Whatever the output coming from the SWAT, that will be the output input for the SWAT curve. Okay. All of you open SWAT curve. And there one green color box will be there. Click on that. Okay. Click on new project. Click next. Here we need to browse the text and out folder location. Okay. Click on browse and go to your ArcMap project folder. Go to your path where you have saved your ArcMap project. Okay. Wait. Okay. I think you have saved the scenario with some name, right? We have saved with sim1. I think you might have saved with some other name. Okay. And see this pink color one. Text now. Okay. Select that one. Click open. Click next. Here you need to choose the SWAT version. Latest version we need to choose SWAT 2012 and processor. If you are using 32-bit, you choose 32-bit. Or else if it is 64-bit, you choose 64-bit. If it is 64-bit, you want to choose 64-bit. Okay. Click next. And next, here we need to choose our project folder. Okay. There one folder will create. And all whatever the results will come in, all those backup results will be for in that folder. Okay. Good. Oh, this is not project type. Okay. Here it is project type. Here these are the different algorithms which were inbuilt in this setup. First one is SUPI2, GLUE, Parasol, Monte Carlo, PSO. Okay, particles of information. So from the literature review, it is observed that when you are looking for a stream flow or sediment yield, for these two, like SUPI2 algorithm is giving best results. Okay, so that's why we are choosing SUPI2. Select SUPI2. SUPI2 sequential uncertainty fitting algorithm. Okay. Next, just create one project name. Just type cup 1 or something. Okay. Next, give project location here. You need to create one folder. Just create one more. Folder. Change cup 1. Okay, cup 1. Okay. Double click on that. Click OK. So all the results of backup will be stored in this folder. Okay. Next, finish. So whatever the texture mount folder there, it will copy paste in this folder. So it won't disturb the original one. Okay. Now whatever we are doing trial and errors, all will done here. Okay, all of you reached here. Now we copy pasted the SWAT texture node folder here. Now we need to tell to SWAT up. So where my watershed outlet is there. Okay, here we need to give our observation data because in the texture node folder there is a simulated data. Here we need to give observation data everything. Okay. So first step is calibration inputs. All of you click on reach. So we are doing on a reach level. Okay. Next, calibration inputs. The first one is parameter information. Okay. Here the basically 4 parameters are came. We need to add some more parameters. It was like almost 21 to 25 parameters are there related to stream flow. Those we need to use. Okay. I will explain how SUPI2 will work. Okay. So what SUPI2 does is it will follow Latin hypercubic sampling. Okay. It will follow Latin hypercubic sampling. So Latin hypercubic sampling means, for example, here one parameter is there. Okay. We need to give parameter and we need to fix the range. Okay. For example, 1 to 100. Okay. 1 to 100. For example, X parameter ranges we have given 1 to 100. Suppose 1 to 10. Y parameter we have given range 1 to 10 again. Okay. So 2 parameters range we have fixed. So what a Latin hypercubic sampling, what it will does is, suppose we gave 50 iterations. Okay. It will divide the X range into 50 equal intervals. Okay, 1 to 10 is a full range, right? It will divide the 1 to 10 range into 50 equal intervals. Okay, means what? Suppose if it is 1 to 100 means 1 to 5, 5 to 10, next 10 to 15, 15 to 20, 20 to 25. Like that, it will divide the full range into 50 equal intervals. We have given 50 simulations, 50 iterations. In the same way, it will divide the second parameter range into 50 equal intervals. Okay. Then what it will take is it will identify the unique parameter set. Okay. From 50 equal intervals, from each interval it will take randomly one value. For example, first equal interval is for x 1 to 10, 1 to 5. So it will randomly pick one value. Again, in the second parameter, in one of the interval it will suppose in the second interval also 1 to 5, it will take randomly one value. Okay, so that will be one unique combination. So model will run with that unique combination. Understood? In the similar way, how many parameters you have given? For all the parameters, it will divide the full range into that many number of equal intervals. How many you have given iterations? Okay. After that, it will identify the unique parameter sets. Then it will perform for each parameter set. Suppose if you have given 500 iterations means it will identify 500 unique parameter sets and model will run 500 times. And it will tell you out of 500 parameter sets which parameter set is giving best results. Means out of with respect to all those 500 simulations, the 50th or 60th whatever it is, that particular number simulation parameter set is giving best match compared to remaining 500. Okay, this is what whole SUPU2 does. Now we will see one by one. Okay, first we need to fix the parameters and then we need to give the parameter ranges. Okay, first we will fix the parameters. For example, first parameter is CL2. There are almost 21 parameters are there, which is related to stream flow. So there are some. So suppose if you want to add some other parameters, some other important parameters also there. Okay. Go to add new parameter, the plus symbol. And one of the most important parameter is soil water availability. Okay, soil water availability capacity. So that will be there in soil related information. That is soil related information, right? So it will be available in the .SOL. And these are the soil, you can say characteristics or parameters, or the soil related parameters. Here we are taking soil AWC, available water capacity, soil available water capacity. It is also one of the most important because based on the available water capacity, for example, what is available water? Field capacity minus melting point, right? So if there is a more space, so more water will occupy. So surface runoff will be less. If that depth is less, then available water capacity depth will be less. More surface runoff will happen. Okay. So that's why it is also one of the important parameters. We have added that soil. Just click OK. And one of the more important parameters is soil hydraulic conductivity. Soil K. Just similar way, go to add new parameter. Just search for soil K. Just below the soil database. Okay, click OK. Okay. We are just taking for the today's just hands-on. We are just taking 6 parameters. Otherwise, it will take time. Okay, 6 parameters. And next one is we need to choose the method. So how we are adjusting your parameters with respect to the baseline period? Are you replacing the value with the initial value? Are you adding the value with the initial value? Are you multiplying are you increasing that with relatively? Okay, that we need to choose. So just keep cursor here, method. Just keep cursor here. just keep cursor here, and question mark. Question mark. Okay, fine, I will help. Yeah, just arrow mark, down arrow. So there are three methods, right? Relative, absolute, and replace. So what will happen exactly? I'll tell you. So before we are performing calibration, we need to look into all these parameters for the uncalibrated model. What is the CM2 value? When we run the model, what is the CM2 value? What is the soil AWC value initially? Okay, those parameter values we need to note down. What are the initial values? Okay, then CK. R relative means multiplies the existing value. For example, I'll tell relative later. Second one, additive. For example, our groundwater delay. Okay, suppose initially it is 10 days are there. Then we are adding, suppose here we will keep the range 15 to 30. After 500 iterations, we got that the best value 1 will come. Suppose it came 20. Okay, if you keep additive means what will happen? Initial value is 10, right? 10 plus 20. So value become 30. So for that 30 model will run. If you keep replace method, that 10 will become 20. Okay. If it is a relative method, what will happen? Relative means it will change minus 100% to plus 100%, right? It may vary from minus 1 to plus 1. Okay. So, for example, you got the value after 500 iterations. After 500 iterations, after 500 iterations, you got value is in between minus 1 to plus 1 you will get. So, for example, you got 0.5 value after 500 iterations. 0.5. Okay. What it will do is 1 plus 0.5. It will become 1.5. So that 1.5 value will be multiplied with the initial value. For example, initial value is 70. 70 multiplied into 1.5. Whatever the output comes, that will be taken for the model run. Understood? For example, I'll tell one more time. It was somewhat tricky. Yeah, I will tell. I will come to how to fix the range. Okay? To understand these three methods, first one is replace. What will happen? Whatever the value which is coming after all the simulations, so that particular value will be replaced with the existing value. Okay? If you have choose additive method, whatever the value which is coming after the simulations, it will be added to the initial value. If you choose a relative method, what will happen? Whatever the value which is, when you are choosing the relative method means that particular range should be in between minus 1 to 1. So we will get one value. Suppose you got minus 0.3. Okay, after all the iterations. So 1 plus minus 0.3 will become 0.7, right? 0.7 will be multiplied with the initial value. So value will reduce. 70 into 0.7. Value will reduce. That reduced value will be used for the model run. Okay? Understood? And for which parameter, which method should be used? That is also one of the main criteria. Okay? Which method want to use? For example, CN2. CN2, why we have to use relative? And when we need to use replace? When we need to use additive? Okay, that you should also have that clarity. When your parameter is varying with respect to HRU, for example, this curve number will be depend upon the crop type. Okay, so these crops will be vary from HRU to HRU. When your parameter is varying with respect to HRU, then how to choose relative method. Okay. When your parameter is constant throughout the subbasin, then you can choose either additive or replace. Understood? Should remember this. When the parameter is varying with respect to HRU, then you have to choose relative. When the parameter is same throughout the subbasin, then you have to choose either replace or additive. Okay. For example, this if you what will happen if you choose replace method or relative method, replace method or additive method for a curve number? Okay, what will happen for each HRU? For example, in one HRU, CN value is 50. In second HRU, one is 70. In the same subbasin, in subbasin 1. So if you try to replace these two, suppose you got 60. Suppose you got 60 after 500 iterations. What will it do? It will replace 50 by 60, 70 by 60. Then that spatial variation will go on. Okay, that's why we are using relative method. So relative means this value will vary from -1 to +1. For example, after 500 iterations, you got -0.3. Okay, 1 minus 0.3 will become 0.7. So what will update is 50 into 0.7, 70 into 0.7. Still you are maintaining that spatial variation. Okay. So you just keep in mind that when the parameter is varying with respect to HRU, use relative method, and when the parameter is same throughout the subbasin, use relative replace or relative method. Okay? In such a way you need to choose this method. Now, so as per the literature review, like all the groundwater parameters, like we have seen, the SWAT was not able to capture all the groundwater spatial variations. So it's what SWAT will assume that throughout the subbasin, groundwater parameters are same. Okay. So this alpha BF is base flow. So use it is also groundwater parameter. So all the groundwater parameters, they are not changing with respect to subbasin. So we can use either additive or replace. So choose replace method. For groundwater relay also choose replace method. Just change that method. Okay. Groundwater QM is also groundwater parameter. Here you can see dot GW means groundwater parameter. Dot MGT means management parameter. Dot SOL means soil parameters. This soil is also varying with respect to HRU, right? So soil is also have to use the relative method. Understand how to choose the methods? Now we have to fix the range. For relative, anyway, that range will be vary from -1 to +1. Okay, but you should not give blindly -1 to +1. That is the full range. Okay, you have to fix, because this -1 to +1 means what will happen? It will do 50 into G, like 0 to it will check. It will test the CN value 0 to 100. So it will take broader range. So that means calibration will take time. So that's why in the calibration, these parameters should not, it won't change much. Okay, 50 suddenly won't become 10, 20. 50 might become either plus or minus 10. That's it. So it won't become 0. It won't become 100 suddenly. Okay. So the variation might be plus or minus 20%, not more than that. Okay. So that's why we are keeping the first rise -0.2 to +0.2. Okay. For CL2. Next alpha BF. Okay. Alpha BF means base flow. How much time it is taking to create to reach the base flow to the stream. Okay. This is you keep either 10 to 15 days. 10 to 15. First one, alpha BF. One more thing I want to tell you. Suppose you just click on this one, absolute SWAT values. It will here all the parameters are there with the full range. Okay, if you don't know, what is the range of parameter? Here you can check. But here the range, it is full range. Here whatever it is giving. Okay, you can check the parameter ranges here, initial ranges broadly from like starting point to ending point. Okay, next coming to groundwater delay. Just keep I think keep 100 to 150. Keep 100 to 150. That's what we this arc map is not working. Actually, if arc map is working, I think no need to do arc map. Huh? Okay. I'll tell you. Okay. Open desktop. Scenarios. Scenario. Text now. Text now. Come on. Come on. Text now. Text now. Text now. Open gw.jw. Any GW. Open it. Notepad. See here whatever the model which we have run initial model, in that it was mentioned that groundwater delay is 31 days. Okay. These are the values you should note down before giving the ranges. So according to that we will change the ranges. Now what are the parameters I am giving now? Groundwater QM. Open it. Groundwater QM. Open it. What is the initial value? And you can see the definition. Threshold depth of water in the shallow aquifer required for return flow to occur. Okay. So you will it is initially 1000 mm is there. Just fix that. So how you need to fix the range is, for example, what our model is predicted, it is predicted over predicted, right? So we need to decrease the surface runoff. We need to decrease the stream flow, right? So you need to know the relationship between each parameter versus stream flow, surface runoff. Each parameter with respect to surface runoff. For example, curve number is directly proportional to surface runoff, right? Now what you need to do, our aim is to decrease the stream simulated flow, right? Because it is overproductive. So we need to reduce the surface runoff. So surface runoff was directly proportional to curve number. So curve number should be decreased. You can see open .mgd operations. What is the initial value? Minimize it. Go to scenarios. Open init.mgd. Go first. Type you can search also. .mgd. Open it, anyone open it. Okay. You can see in this particular HRU 25.5, the value of curve number is 77. So what we need to do now? Our aim is to decrease the curve number, so that it will, because it is directly proportional to stream flow, surface runoff. So, okay, just minimize it. Minimize it. That one. Now here, just keep it here. So what we have kept to minus 0.2 to plus 0.2, right? This is our initial range. But we have a clarity that we should decrease the surface runoff. So if you want to decrease the surface runoff, it should come negative, right? Because we are using relative. It should come negative. So no need to keep positive here. You can keep minus 0.1. Understood? Why we are keeping, why we are limiting to only negative range? Because if you keep minus, just keep minus 1 here, minus 3 to minus 0.1, minus 0.3 to minus 0.1, minus 0.3 to minus 0.1. So even if you run 100 simulations or how many number of simulations, the output should come in the negative, right? So the negative value will be multiplied here, the curve number will decrease, automatically stream flow will decrease. In the same way, you need to identify how the each parameter is relation with the stream flow. Okay, alpha BF, base flow. Base flow is the inversely proportional to stream flow. The base flow is it was immediate response, so surface runoff will decrease. In the same way, soil hydraulic conductivity. If your soil hydraulic conductivity is very high, so that means what? Runoff will be less, because soil is having high infiltration. So runoff will be less. So you can also check what is the value of soil hydraulic conductivity for the model which we have run, and we need to increase that hydraulic conductivity so that our stream flow will decrease. So if I want to increase hydraulic conductivity, first you should know what is the value initially there. Just check what is the initial hydraulic conductivity soil K value. Go to scenarios. This dot SOL. Open notepad. The parameter how it is relating with the stream flow. If it is directly related, if it is directly proportional, then if your aim is to decrease the stream flow, that parameter range also should be decreased compared to the base value. Okay. In the similar way, you need to arrange all the parameters. Then you can also you need to mention here how many number of simulations you want to keep. Generally, we have to keep minimum for each parameter. We need to keep 100 simulations. Means suppose if you are using 6 parameters, you have to keep minimum 600 simulations, so that each interval will be equally divided into 100. It will divide into 100 equal intervals. Basically, if you increase the number of simulations, it will take each and every minor value and it will test the model. So you will get the accurate, means you will get the results in accurate. But it will be computationally, it will take more time. If you keep 500 simulations also, it will take almost 10 hours. It depends upon your system. In 32 GB RAM, here it is taking, for 500 simulations, it is taking almost 8 hours. Depends upon. It depends upon basin area also, number of HRUs also, and the time period also. If your time period is less, it won't take much time.
The initial curve number is 70. In absolute swap values, the range is between 35 to 98. So why can't we give?
That's what it depends on the method what we are choosing. They kept how the CM2 value will vary. Generally CM2 value, the full range is 0 to 100, right? Generally it won't be, in a concrete phase it is 100. Okay, but generally it will be, the main range is 32 or 80 or 90. So that's why they kept like that. If you want to, even after, if you are using the relative method, that's why we are keeping in between -1 to 0.1. So -1 to +1. Finally, you will get one value. That value will be added to 1. That you are multiplying with the initial value. Again, simple. Again, after running this, suppose for example 50 into -0.3, what will happen? 30 that you are using. Also have its own readable format, so we have to give in the same format. That is what next we are preparing that only.
And one more doubt. On parameter related to groundwater,
parameter is varying with respect to HRE.
Okay, okay.
Groundwater will, the SWAT it will assume that groundwater parameters all will be same, it will be uniform throughout the survey scope.
Okay, for 1000, what is the minimum value? What is
That's
the
what.
maximum value?
Now you see, for example, 1000, right? Groundwater payment. You try to understand what is the parameter relation with the stream flow. Okay, for example, if it is directly proportional, okay, now you want to decrease the stream flow. So that 1000 should be less than 1000, right? So you should fix, you can keep anything, any range less than 1000. So you can keep 500 to 900. So
That is replaced.
method is replaced.
Okay.
So it will be fall definitely within the 500 to 900 value. Okay, so definitely automatically our flow will decrease. But the main thing is here we are doing all parameters changing at a time, right? We are changing all the parameters at a time. So because of one parameter effect on other parameter, even though you are trying to reduce the CO2 value, sometimes stream flow won't decrease because of the other parameter effect. Okay, that is also there. That's where first we need to try to identify the sensitivity analysis. This SWAT cup, the main advantage of this SWAT cup is it will also perform sensitivity analysis. So it will tell you what are the sensitive parameters. So you can change only those sensitive parameters for the next iteration.